So today we'll have log plot lab review. In this lab you'll learn about an application of a population model. In an example in this lab, it's an observed population of United States from 1790 to 1900. So suppose we have these data and we ask a question of what the population would be in 1910. So the method we are using here is we can draw the graph, plot the data, and try to fit in a curve in the data. And the next point in the curve will be our guess for the population in 1910. So how do we do that? First, I copy the data in Google Sheet, right? And then we can plot the data, and we will try to fit a curve. In this case, we'll fit a trend line. Google Sheet offers 6 kind of trend lines. So linear means we're trying to fit a linear function in the set of data. So we try that first. Of course, it doesn't work because it's not a line. And we can try exponential. So exponential quite fit the data. We can try polynomial. It works. I think it works better. You can try logarithmic, right? It doesn't work. And power series does not quite work. So we have 2 candidates. One is exponential and the other is polynomials. How do we know that which model is correct, right? Either the function has to be polynomial or exponential. So our second job is to find the correct model, right? So to do that, we'll study a population model to see what the population would behave, what the function it is, right? So suppose now we have a toy example of an observed population of, say, a C at the observed year, which is year 0. We have 5 million. And the birth rate, or in the increasing rate, is 1% every year. That means, say, after the first year, the population is 5 multiplied by 1.01 million, right? So at the beginning of the second year, or the end of the first year, we will have this many people, 5 multiplied by 1.01. And after the second year, we will have 1% more than that. So which is 5 multiplied by 1.01, which is in the beginning of the second year, plus 1% of that amount is 0.01 multiplied by 5 multiplied by 1.01, and the result is 5 multiplied by 1.01 square. So that's at the end of the second year. When we enter the third year, 5 multiplied by 1.01 square will be the population. And after the end of the third year, we'll have to add 1% of that. So which is, as we calculate here, it's 5 multiplied by 1.01 cube. And we can do the same for the fourth year. So after the fourth year, we'll have 5 multiplied by 1.01 to the fourth million. In general, we can generalize it. After t year, we will have 5 multiplied by 1.01 to the t. And it is an exponential function. So let me explain why it is an exponential, right? Because exponential we mean e to the something. Why here we have 1.01. So first, in general, we have the form of a multiplied by b to the t, where a is 5 in this case, right? And B is 1.01, and T is year. Now that's a general population model, population of the city. Now we can change it into e to the something by noting that b is actually e to the ln of b, or e to the log b. So we can change a multiplied by b to the t to a multiplied by e to the t multiplied by ln b, which is this function. So we can write our population as a function in t as a multiplied by e to the t ln b, right? So our job here is to find a and b. So once we know a and b, we will know what our function pt is, right? Then we can plug in and say find pt plus 1. In this case, it's p of 120, which is 120 years after 1790. So after 120 years, which is 1910, that's what the population would be, right? So again, we have to find a and b, and how do we do that? It is hard if we just look at the curve and see what a and b is. So our trick here is to transform this curve, this equation, into something nicer. So that's the purpose of this lab. The observation is that the log function we transform a product into a sum. So if we take log of pt from the left, on the right we will have log of a plus t log of b, which is the equation of a line. So for example, we do in year 0, we take log of the population, we got log of 5. At year 1, we will have log of 5 plus log of 1.01. In year 2, we have log of 5 plus 2 log of 1.01, etc. And in general, we have log of 5 plus t times log of 1.01. And if the equation is a times b to the t, the equation of the log population is a plus t log b, right? So instead of looking at a curve, now we have a line y, when we have y represent log of pt and x represent t, as we have here. So our pt has a form a times e to the t ln b, or log b. Then if we take log, it will be log of pt equal log of a plus t log of b, and it represent y as log of pt and x as t. Then we will have a line. It's y equal to, if we do that, then it will be y equal ln a plus x times ln b. So that's a line that we have, and ln a is y-intercept, right, in our line, and ln b will be this slope. Okay, so that's our conclusion. Now let's work on the actual example. In this example, I will do log of the population. So this one, 1.36, is log of 3.9, 1.66 is log of 5.3, and etc. At the end of 110, 4.33 is log of 76, right? So then we'll plot this data, we'll have this chart, and again we can find the trending line, which is linear. Because we know that it is linear here. We know that the equation is a linear one. So after finding trending line, we can find y-intercept. In this case is 1.33, right? And the slope of this line is 0.027. It doesn't look like 0.027, but you can look at the y-axis and the x-axis. The x-axis is from 0 to 25, when the y-axis is from 1 to 5. So that's why this one looks steeper than it actually is. Okay, so we find the line. We found the y-intercept and the slope. So y-intercept is 1.43 and slope is 0.027. Now we can plug in to our equation. That means log of A is 1.43 and log of B is 0.027. Right? Or that means A is 4.39 and B is 1.027. Then our equation PT now is 4.39 multiplied by e to the 0.27t, or 4.39 multiplied by 1.027 to the t. Now if we plug in t equal to 120, then our p is 4.39. Oh, I need to write the equation. 4.39 multiplied by 1.027 to the 120. Now we get the result, which is 107 million. That would be our prediction. So you will apply this method to do part 2, the completion of the experiment, and you'll do the exercise 1 and 2 here and write the report.